All right, well, good Wednesday morning. Welcome to another fun-filled day of Math 105. Today our plan is to keep looking at applications of derivatives, things that we can use them for, because last time, I guess the last two times, we've looked at related rates as an application, so how we can determine how one quantity is changing with respect to another. And today we're going to just look at more applications. We're going to look a little bit more at the idea of using the tangent lines as approximators. We kind of did that a while ago. I'll remind you about that. But we'll look at that, and we'll actually start looking at what derivatives and all that tell us about graphs. By the time that we're done with calculus, with this class, you'll be able to draw really, really, really good graphs, even without a calculator, using nothing but algebra and calculus. So we're going to start into that today as well. But before we go into that, are there any questions about homework or anything else that we've been talking about?
Can I ask a question about logarithmic differentiation?
Sure, go for it, Alia.
Would you be willing to just work through f of x, excuse me, f of x equals x to the 4x?
Absolutely.
Thank you.
All right, so let me go ahead and go back to a whiteboard here. Clear this other garbage because don't need that right now. Okay, so let me just make sure I got it. So it was y equals x to the 4x?
Yeah.
Okay. And this is just we want y prime, right?
Yeah.
Okay. So we're looking for what is the derivative of this? So you look at it and you go, okay, cool, exponential, I can use the exponential rule. No, you cannot because of this variable down here. So then you might go, okay, cool, power, I can use the power rule. Nope, because of this power up here. Unfortunately, we can't use either one. So instead, what we're going to do is do logarithmic differentiation. So let's take a natural log of each side. Now, by doing that, we're now going to be able to use the rules of logs on the right-hand side here. So we've got the natural log of y equals 4x times the natural log of x. So the rule that we use there was the power rule of logs, right? That an exponent comes out front as a multiple. All right, so how are we at that point, at this point? So far, so good?
Yeah.
Yeah, all right. So now let's differentiate both sides. So we'll go ahead and just do a d dx on each side here. So the natural log of y, since y is a function of x, we have to use the chain rule on this. So natural log gives us y on the bottom, and then the derivative of y on top. So hopefully you're getting pretty comfortable with logs. Natural logs are beautiful. Whatever's in the natural log goes on the bottom, and the derivative of that stuff goes on the top. So there's that guy. And then on the other side, we have to use the product rule. So I've got 4x times natural log of x. So we're going to get 4 times the natural log of x plus 4x times 1 over x. The derivative of 4x is 4. The derivative of natural log of x is 1 over x. And that's just the rule for power, for products. All right, so now all that's left is to get y prime by itself. So I'm going to multiply both sides here by y. So I'm going to get 4 natural log of x plus 4. And all of that's going to be times y. But having y here is not preferred. but luckily we know what y is equal to x to the 4x. So we can go ahead and substitute that in. And so that right there is the derivative of x to the 4x. All right, so logarithmic differentiation, it's kind of a nice little trick because it turns it into a form that we know how to deal with. Anyway, so Ollie, is that good? Yeah, got a thumbs up on that. Awesome. All right, any other homeworky kind of questions? All right, well, hearing none, then I'm going to go ahead and hop up to the whiteboard and we'll keep talking applications of the derivative. So I'll be right back. All right, so last time, well, the last couple times, we've been talking about related rates, which is a huge application, but there are so many more that's really what this entire chapter is about, or just different applications of derivatives and what we do. So let's kind of continue on with things that we can do with the derivative. So we're going to start basically with the fact that derivatives are good approximations. And so we're going to go with derivatives and linear approximations. This is kind of our next kind of bigger topic, is what do derivatives do in terms of linear approximations, and what does that even mean? Okay, so first of all, just think about the naming of things. So linear approximations, what this is going to be approximating a curve with a line. So instead of having whatever random function with whatever kind of waviness, curviness, instead what we're going to do is we're going to approximate it with a line, hence linear approximation. Okay, now, before we get to what derivatives have to do with this, maybe the next question is, well, why? Why do this? Why actually take a function and instead of looking at it as a whole thing, looking at it as a line? And really the reason that we're going to do this is because lines are easy. I'm even going to give that an exclamation mark. They're easy. We know everything about them, right? If you want to draw the graph of one, all you got to do is, know 2 points. Or if you know a point and a slope, the slope tells you what direction it's going. Once you start going in the direction, you never stop, right? They're really easy to draw. They're easy to calculate with, right? Like think if I give you an equation of a line and I told you what's y when x equals 4, it's super easy calculations. All you've got is add, subtract, multiply, and divide. You don't have powers, you don't have roots, you don't have anything. So lines are super, 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 super easy. All right. And especially in a world where you might not have your technology, and this is where you kind of have to go back in time and think about when calculus was invented, right? We're talking almost 400 years now. Back then, we didn't have all this crazy technology. They had to do things by hand. Yeah, we're going to go to a line. Now, before you go, yeah, but I've got technology now. And there are still instances where being able to do linear approximations much faster and much easier and better, right? So just always keep that in mind. Don't get to the point where you're just like, I've got technology, I'm good. Not always, right? Or there still can be faster ways. But this is the goal. Basically, we're going to take functions, and instead of the functions themselves, we're going to think about lines that approximate those functions. All right, so what does the derivative have to do with this? Well, you already kind of know. Back when we were first learning about derivatives and we were talking about graphs and rates of change and all that, when we had some sort of a function here, and we looked at the derivative at some point, that derivative, let's say this was c, and so we found this point right here, that derivative gave us the slope of this tangent line. Well, that tangent line, that's the line we're going to use for our linear approximation. Okay, so I'm going to put here, use the tangent line. If you were to zoom in on this graph, like just keep zooming in, get closer and closer and closer. So, put this into Desmos, put this into your TI-89, whatever your favorite graphing modality is. Draw the graph of this and start zooming in. And eventually, that graph is going to look really linear. And in fact, the closer we get to this point, the more and more linear the function actually looks. And that was even the rationale for using linear approximations, is that, well, if you get close enough, it looks linear. All right, so we're going to use that tangent line. That's why we care about the derivative. And that's what this has to do with why this is an application, is this derivative gives us the slope. We also have a point, conceivably, and that point and that line is enough for us to, or that point and that slope is enough for us to get the equation of that line, and then we can use that line. All right, so I've already shown you examples of this. I want to remind you of one. And this would be something like, what if I asked you, what's the square root of 99? So that's an easy question. What's the square root of 99? What number, when we square it, gives us 99? You
9 point something, less than 10.
So it's going to be 9 point something. It's going to be less than 10. Hey, Suzanne, how'd you get that? How did
Because
that come in mind?
10 squared is 100, and it's not there yet.
Okay, no, that's beautiful.
But it's greater than 81.
So you can hear there's a little bit of in your mind, in your voice is coming out the little chuckling that's in your mind, and you're like, it seems sort of like a silly answer, but no, that's the perfect answer. You know that it's not quite the square root of 100. Square root of 100 would be 10. So you know that it's going to be under 10. You also know it's going to be greater than 9, because 9 squared is 81.
Also greater than 9.5.
You're using the intermediate value theorem, by the way, FYI. Right, and so yeah, I mean, we can all probably agree that that's going to be 9 point something, and that 9 point whatever is going to be kind of on the big side, right? 9.8, 9.9, somewhere in there. So we at least have a ballpark idea. We could use a calculator, we could use technology to actually get something better, but let's just pretend for a moment that we don't have all this lovely technology that's allowing me to come to you in your living room, wherever you are in the world. Okay, so we're just going to pretend we don't have any of that right now. We can still get a decent approximation for this using the tangent line, using the derivative. Okay, so here's kind of how we want to think about this. We've got the graph of the square root. And if this picture looks familiar, it should, because I kind of used this as an example a while ago about why we care about the derivative. It wasn't the square root of 99. It was like the square root of 4.1 or something. But it was the same kind of idea. So we've got the square root function. Somewhere over here is 99, right? But 99 isn't a nice number. A nice number for us is going to be 100, because we know the square root of 100. Oh, that's just 10. So somewhere over here is 100, and we can get the tangent line at 100. And this isn't quite showing you the disparity that I wanted it to show you, so I'm going to cheat a little bit here. And so the actual value we want is on the red line, and I'm going to mark it with this blue dot. Right? That's the actual square root of 99. But instead of getting that value, we're going to use the line. And there's a green dot on this line. And that green dot, if we can get its y value is going to be close to the square root of 99. And that y value is going to be a lot easier to find because it's a line, right? Lines are easy. We can plug anything into a line and actually get its equation. All right, so here's what we're going to do. Think about the derivative, dy dx. Right? It's going to be a slope, so that's going to be our m. That means that the change in y, the actual change in y, so if we think of it as delta y over delta x, this is going to be approximately equal to dy dx. Now, let me real quick, I threw on the little triangles, the deltas. So delta y and delta x, those are the actual changes in the function value. So if we go from this point where we calculated our tangent, the delta y is this right here. It's the actual difference. It's the actual difference in my function value. That's what I mean when I say delta y. The delta x is how far we're going in the x direction to get to that other actual value. Okay, so you notice how I wrote here that this delta y over delta x is approximately dy dx. Because delta y over delta x, that's the slope of the secant line. I'm just going back to the language that we used before. So this is the slope of the secant line. This is the slope of the tangent line. So they're not equal, but they're close. And in fact, we know that they're going to be closer when that delta x gets smaller. If we take a smaller step, then those two numbers are going to get closer and closer together. I mean, that's basically how we developed the derivative anyway, right? Secant line slope, and we just brought those 2 points together. All right, so if I rewrite this just for my delta y, I find that delta y is going to be approximately equal to, and I'm going to write it as f prime of x just because I think we're getting too many of these little d things. But here, what I just circled there in blue is basically everything that ever happens when we do linear approximations. All right, we're going to see that the actual change in y is going to be approximately equal to the derivative times our horizontal step. Right? This is using the fact that the line has this relationship, and the approximately equal is our approximation. Okay, so all this stuff, whether it's we're finding the square root of 99, or we're doing error propagation, we'll talk about that later, or anything else that's using linear approximation, it all comes back to this statement right here. Okay, and it's really just slope. Slope is change in y over change in x. I'm just solving that for a change in y. Okay, so let's get back to this idea of the square root of 99 and actually use this linear approximation. So we need a function, and obviously the function we're using here is the square root function. So what we need to do is we need to differentiate it. Okay, well, if f of x is the square root of x, then f prime of x is 1 over 2 square roots of x. Turn it into a 1/2 power and do the power rule. We've done this enough that hopefully at this point you go, oh yeah, I kind of remember seeing that. But there's the derivative. Okay, so let's use a point near 99 that we know. In this case, it's going to be 100. So if we were to do f of 100, the square root of 100 is 10. If we do f prime of 100, that's 1 over 2 times the square root of 100, or 1/20th. So 100 is a nice point. We're able to figure out exactly the function's value there and its derivative. But now let's use this linear approximation. So we know that the change in the function value is going to be approximately equal to the derivative, so 1/20th, times the step away that we're taking. All right, so now this is where we're going to look at the value we're really trying to find and compare it to the value that we found. So we're looking for the square root of 99, right? And we're going to compare that to the square root of 100. So how far is 99 from 100? It's like the easiest question I've ever asked.
1 away. Minus
Okay,
1.
so it's 1 away. So that means our delta x is either going to be plus or minus 1. Well, we just have to think about how far are we going, which direction are we going from the point that we know. So since we're going from 100 to 99, our delta x is going to be -1. Okay, so this was our f prime, and this was our delta x. If we had been going for the square root of 101, delta x would have been +1. If it was the square root of 103, delta x would be 3. Square root of 95, delta x is -5, and so on. So delta x is just telling us how far do you go from the point that we know about, 100. How far do you go from that point to the other one? And you make sure that you keep your sign telling you whether you're going left or right. All right, well, multiplying these together is super easy. So we get -1/20th. All right, so what does this mean? Well, this means that the change in the function, so the difference between the square root of 100 and the square root of 99 is around -1/20th. The square root of 99 is about -1/20th less than the square root of 100. Okay, that's how to interpret this number. So that means once we put this all together, the square root of 99 is going to be approximately equal to the square root of 100 minus 1/120th. So whatever we would have found for our delta y, we're going to add that to the square root of 100. All right, well, we know the square root of 100 is 10. 1/20th is 0.05. So this is 10 minus 0.05, or 9.95. So the square root of 99 is going to be around 9.95. It's not exactly 9.95, but it's going to be close. And all of this was done with no technology. I mean, you saw me do it. This was the extent of the technology that I used, other than the computer in my head, right? But no technology, and I know the square root of 99 is around 9.95. All right, so I know you guys have technology available. Use your calculator. What's the square root of 99, according to your calculator or computer?
9.949874371.
9.9498.
74371.
Okay, so according to whatever calculator or thing that Susanna used, she gets told that the square root of 99 is 9.949874371. Obviously, it's going to keep going on. How'd we do?
Good, because we rounded to 2 decimal points.
Yeah, 9.95 versus 9.94987. I mean, we are good within 0.02, 0.0002. So that is 2 10,000ths. We're within 2 10,000ths, people. That's a damn good approximation. So, and this is what the mathematicians of the time figured out. They're like, man, now all of a sudden we have a quick and easy way of figuring out these values so that we can be close. Even if we don't know exactly, we can be pretty close. And even in today's world, 9.95 versus 9.9498743, you're probably pretty good. I mean, maybe not if you're sending something to Mars, right? But for the most part, like any kind of an engineer is going to be totally fine with that kind of tolerance. Right? Think about what percent error is that? If the actual value is 9.9498, whatever, and you're only off by 0.00013, it's such a small percentage of error that you'd be more than happy. All right, now I showed you another one with a square root, and so you're probably like, yeah, okay, so it's work for square root. Let me show you another place where we could use this. Let's do this. What if I asked you a different question? Oh, actually, before I go there, questions on this one? How are we feeling about it? Are you at least impressed? Are you impressed at how close we got?
Yes.
Yeah, I'm seeing some thumbs up. You should be impressed, because that's pretty amazing, right? I mean, just, we haven't really gone that far into calculus. Probably feels like we have, but we haven't. And yet you're already starting to see the power, how useful it can be. So anyway, all right, so here's another question. What if you're doing your thing, doing your whatever, and you find out that you need to know a value of cosine of 0.2.
0.98.
Let's not do cosine. Let's do sine. Sine's a little more interesting. Okay, so we want to know the sine of 0.2. So what kind of angle is 0.2? Small. That's the best answer I can give
Positive.
you right now, right? But it's a small angle, but definitely not 0, right? 0.2 is sufficiently different from 0. So the question is, what is the sine of 0.2? Now, let's hold off on going to the calculator. Let's start with, let's use calculus to see what's going on. All right, so basically here's what we have to do. If you think about what we did over here, we need to have a function so that we can differentiate it. And then we have to have a point, hopefully kind of close to where we are, so that we can use that to evaluate the change and get a guess. Okay, so what's my function?
Sine of 0.2.
Okay, so it's going to be sine of x, right? We're plugging into sine. So let's let f of x be sine. So of course we know its derivative. The derivative of sine is cosine. All right, so now we need to have a point that's kind of close to 0.2. So anybody have a point they would like to use that's near 0.2?
0.
You guys good with 0? Seems pretty close. So let's do that. Let's go with 0. All right, so sine of 0 is 0. The cosine of 0 is 1. So we put this together, we get that delta y, so the change in the function value, is going to be approximately equal to f prime of 0 times delta x. So f prime of 0 is 1. And what's my delta x? All right, so Bailey just put in the chat box 0.2. Good. It's going to be 0.2. Because remember what delta x is. Delta x is how far are we, the actual, where we're really looking, how far is that from where we're calculating our slope. So we chose the point 0 because it seemed nearby. So from 0 to 0.2 is 0.2, and it is positive because we're going to the right. It's getting bigger. Okay, so 1 times 0.2 is 0.2. So that tells me that the sine of 0.2 is going to be approximately equal to 0 plus 0.2. So the 0.2 is what we just calculated. And where did the 0 come from?
When we use 0.
Well, be careful. It's not the 0 that we were plugging in. It was
a sine of 0.
Right. It was the 0 that came out. So it was the function value at that point. And we added our delta y. Okay, so that tells me that the sine of 0.2 is really close to 0.2. All right, so Suzanne, I know you've got something handy. Can you calculate for me the sine of 0.2 in radians?
0.19866933308.
Okay, so 0.19866 something, something, something. All right, how'd we do?
Really good.
Still feeling good about it? Right, I mean,
Yes.
this isn't nearly as good as the square root of 99. Right, square root of 99, we were good, like way far out. But this one, we're still only off by about 0.002. It's
But
a
if I was to
1%.
build something in engineering, this like it wouldn't matter because like it would look the same.
Well, yeah, so this is a 1% error, basically,
Uh-huh.
right? Plus or minus 1% for the most part. I mean, I can at least tell you from the science world, we're all on board with that, man. You get within 5%, you're happy. But again, really, really good approximation. Okay, but let's do this before you get all, yes, this is easy. What if instead of sine of 0.2, I wanted to know the sine of 1? All right, so I mean, we're going to use the same function and everything, but let's just say we go to sine of 1. So we could literally use the exact same thing. We're using sine, its derivative is cosine, and let's even go to 0. If we were at 0, then this one's going to tell us that delta y is approximately equal to f prime of 0 times delta x, which again is going to be 1 times, but in this case, delta x is 1, because from 0 to 1 is a step of 1 away. And 1 times 1, of course, is 1. So that tells us that the sine of 1 should be around 1. So it's the same exact idea. It says, though, the sine of 1 is equal to 1. All right, Susanna, what's the sine of 1?
0.8414709848.
Okay, so now we're seeing that the sine of 1 is actually 0.84, 2 more digits?
17.
Okay,
I
cool.
mean 14. It's 0.841447.
Okay, we'll go that far then. Okay, so it's 0.84147. So now, how do you feel? What do you think about that approximation?
Still decent.
All right, so still decent.
I mean,
I would argue that
it's not the best, but it's workable.
ish. I'm kind of with Era's just put in the chat, not good. I'm not happy with this. Because now think about it, what if we just think percent error? Now I'm off by 0.16, right? And 0.16 as opposed to 0.84, that's like 20%. That's starting to be a big discrepancy, right? And what's happening is we're getting far enough away that that line doesn't really approximate the function anymore. Like, think about the graph of sine. You all know it. You all love it. Sine of x is beautiful, right? Does something like this. If we were to look at the tangent line at 0, pretend that that's a line, but there's my tangent line. And you can see that when we are close to 0, even on my graph, the black line and the red sine are really, really close to each other. But eventually, they start splitting. And that's what happened here. Now that we're out at 1, we're far enough away that we're starting to see this discrepancy. The fact that those two values are considerably different. So this other thing I want you to remember is that when you do a linear approximation, you need to be close. When you choose the point that you're going to use as your, this is around where we are, you need to be close. You need to actually be close to that value. So me personally, I wouldn't have used 0 here. I would have thought about, well, what kind of a value, nice value for sine, do I know that's closer to 1? Well, the nice values, think about the angles that you know the trig functions for. Pi over 6, pi over 4, pi over 3, pi over 2, right? All those guys. One of those is not far from 1. Which one's kind of close to 1? Yeah, how about pi over 3? Pi is 3.1415926, blah, 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 right? Divide that by 3. That's 1.04 or something or other. So if I was going to be doing this, I would still approximate it, but instead of going at 0, I would go, let's look at x equals pi over 3, because it's pretty close to 1. So now we're going to have f of pi over 3. So the sine of pi over 3. And we're going to have f prime of pi over 3. Okay, well, that's cosine of pi over 3. So those are root 3 over 2 and 1/2 respectively. But now when I go and I calculate this, my delta y is going to be approximately equal to, again, it's going to be f prime of pi over 3 times delta x. So that's going to be 1/2. And then my delta x is pi over 3 minus 1. We'll just leave it like that for right now. But we could get a decimal approximation for it if we wanted, right? Pretty easily. Okay, so then that tells me that the sine of 1 is going to be approximately equal to root 3 over 2 and then I need to add to that the 1/2 pi over 3 minus 1. But I think I made a mistake. Anybody see what my mistake is?
Why are we adding?
Okay, so like, why are we adding right here?
Yeah.
Because we always add on our delta x.
Oh, well, shouldn't it be subtraction if 1 is less than whatever pi over 3 is?
Okay, yeah, and that was my mistake. This should actually be 1 minus pi over 3.
Yeah, that makes more sense.
Yeah, that was definitely the mistake I made, because 1 is to the left of pi over 3. So we're actually doing a negative step to get from it. Here on your real number line, guys, here's pi over 3, and here's 1. So my delta x needs to be negative. So sorry about that. I got all excited about doing this thing. All right, so here is then the approximate value of sine of 1. But I know what a lot of you are thinking. Well, first of all, you're thinking, oh, what the hell is going on here? But if you get past that, then you start thinking, but Bruce, you were saying the whole point of this is to be able to get numbers without using technology. And I'm going to kind of have to use technology to get decimals for these guys. Well, back in the day, they knew lots of decimals of pi, just like we do. They knew lots of them. They didn't have, billions of decimals like we do now, but they had plenty. And if I just told you 3.1415926, let's just go that far, you can divide that by 3. You can subtract that from 1. You can divide that by 2, right? You can get a decimal for that. Same thing with the square root of 3. They knew the square root of 3 pretty well. It's like 1.69 something. But you could also get an approximate for that using similar process to what we did with the square root of 99, right? Anyway, so they had those decimals and they could still do this. This is going to give them a much closer value for a sine of 1. So if you were to use your technology on this guy, you're going to get a number that's much closer to that 0.84, whatever it happened to be. Okay, so it doesn't matter what function you've got. You just want to make sure you're close. You want to be at a point that you know, so you can evaluate the function there, you can evaluate the derivative there. But you want to be as close as you can to where you're making that initial guess, because the further away you get, the less this line approximates the function. All right, so this is another big use of the derivative, for sure, because you can use the derivative to get you this change really easily. Just take your derivative times your step, and that will be approximately the change in your function value. So these guys have names, these little dx's and dy's, and they're called differentials. So all the time we've ever used any of these little things, the dx, the dy, the dt, and so on, those things are what we call differentials. And we use these all the time. And when we're doing linear approximations, we're basically using the differentials to approximate the actual change. So you know how, like, I wrote here, delta y is approximately equal to f prime of x times delta x. If I went to differentials, this turns into an equals. Those things are now actually equal. So the differentials are what we use to approximate the actual change, right? What we're saying here is delta y is approximately equal to dy. It's approximately equal to the differentials. So if you ever hear that term differential, that's what we're talking about. We're talking about those little pieces, the dy, the dx's. Those are differentials. Okay, so linear approximation now. That's your second thing that we use this for, use derivatives for. So let me show you another one that's similar to this. And this is actually good for you science types. And this is error propagation. Okay, so when something propagates, it gets passed forward. And so error propagation, what this is, here'd be an example. Suppose that what we're doing is we get hired by the casinos to make dice, right? So we've got a company, we make dice for playing craps. And so the casinos are like, all right, we need the dice to be with these specifications, right? This given weight, given size, and so on. So maybe they tell us, all right, the dice need to be such that each side is length 1 inch. All right, but just because of how manufacturing works, we can't guarantee that it's exactly 1 inch long. But what we could say is, well, it's 1 inch, but plus or minus 1/10 of an inch, right? I mean, think about how often you see that kind of terminology anywhere, where there's places, you know, they'll say, you know, such measurement plus or minus a little bit. That's just potential error. Obviously, we do everything in our power to minimize that, to make that error not exist, because clearly, if we are not very good at making dice that are close to 1 inch cubes, the casinos aren't going to hire us to make dice, right? So we need to be pretty precise, but there's always going to be a little bit of an error. And in science, we totally know this. Like, no matter how good your measurement device is, there's always potentially plus or minus a little bit, right? You've got your sample of sulfur. You put it on the scale. And so, okay, so its mass is 17.3 grams. Yeah, it's 17.3 plus or minus a little bit, right? Just is. So the thing about errors, though, is that if you make an error in one measurement, it can lead to errors in other things, right? Let's go back to the dice example. So if we're off on our length by a little bit, here are other things that we would be off on now. The surface area, right? If our lengths are off a little bit, the surface area of this die is going to be different. The volume's going to be different. The mass is going to be different. Make your list of different quantities. Those are all going to be different. And so any error we make at the start gets propagated, gets passed forward, and becomes an error in other things. Okay, so what we're going to do is we're going to look at how can we use calculus, how can we use derivatives to help us figure out what this error becomes later. All right, so let's go to that die example. So for example, we're constructing dice. And we're going to go metric, because we're going to go metric. All right, but we're going to be constructing dice with the side length of, let's go 2.5 centimeters. All right, but there's possible error. And let's say that we're going to be off by a millimeter potentially. Okay, so plus or minus 0.1 centimeters. So think about it. I don't know if you have a feel for how long a millimeter is, but a millimeter is tiny. It's actually pretty small. And so, I mean, that's decent. That's not terrible, but let's just say that we could potentially be off by 0.1 centimeter. So here's what I want to know is, what is the potential error in the volume? Right, because if we measure that length and we're off by a little bit, our volume is going to be off as well. So that's the question. So let me just turn this to you. How do you think we could calculate this? And I don't even necessarily mean using calculus. If you were presented with this question, And your boss is like, "There's the only way you're getting paid is if you tell me the answer to this." You have any ideas on how you could figure it out?
Calculate the volume of the dies, 2.5, and then 2.4, and subtract.
Okay. Yeah, that's a great way. That's one way that we could do this that uses no calculus whatsoever. Right. So for those of you who didn't quite catch what Mariola said is we could go ahead and calculate what the actual volume should be with the 2.5. Right. We got that length. Let's find the volume. Then we could look at, well, what if the length is only 2.4 centimeters? We could calculate what the volume would be there. And then we can compare them, right? To be good about it, we should probably also look at what if it's 2.6. What if we've made them a little bit too large and actually calculate the volumes? So that is definitely something we could do, right? So basically, here'd be the true volume. So the actual is going to be 2.5 cubed, right? Because volume is equal to x cubed. So the actual volume would be 2.5 cubed. Right? But then if we look at what are the possible, I'm going to call these the worst case scenarios. Would be where we're off by the entire millimeter on each side. Right? So then the volume here would be 2.6 cubed, 2.4 cubed. And we could actually just compare those numbers. Right? So this would totally work. We'd know exactly worst case scenarios, how far are we off from our volume? And in reality, we're probably going to be somewhere in the midst of all that, right? Because one side might be a little bit longer, the other one might be a little bit shorter, right? But this would definitely give us the far extremes. Okay, cool. Thanks for that, Mariola. I'm glad you saw that would be a way that we could actually do this. Now, I don't want to have to do these calculations. The thought of cubing 2.6 by hand, yeah, I can do it, but it's way too early for that nonsense right now, right? I don't want to have to tax my brain like that. So instead, let me show you how we could use calculus for this. Well, we have a formula for volume, right? V equals x cubed. What we're looking for is actually a delta V. What's the change in the volume if I'm off by a little bit? So we can use the exact same thing that we did before, the linear approximation. I can calculate the derivative pretty easily. But now in the context of what these all things are, this delta V, this is the error in the volume. The delta X, this is the error in the length. And I know the error in the length. I was told by the specifications that I'm off by at most 0.1 centimeters. So let me show you how we can use this to get a fast approximation. So f prime of x is 3x squared. And again, we're going to multiply that by delta x. So what I'm going to do is I'm going to put in the actual length that I wanted, 2.5 centimeters. and my delta x. So I'm going to carry that on over here. So here's what my delta v is going to be approximately equal to. It's going to be 3 times 2.5 squared times 0.1. I'm not going to worry about the plus or minus right now. I'll just throw that in at the end. It could either be off by more or less. All right, so now we can do this multiplication, and this one's not terrible. 2.5 squared. All right, that's going to be 6.25. Times 0.1 is 0.625. Times 3 is 1.875. He says without a lot of confidence, so please check my numbers on that. Yeah, I think that's pretty close.
Yeah.
Okay, so I know, just going in, that I could be off by around 1.875 cubic centimeters. That was pretty fast. And it was something I could even do in my head. These other ones, like I could actually get those numbers. It'll take me a little bit longer. And when I look at the differences, you're going to see that the differences between these worst case scenarios and the actual volume are actually quite close to 1.875. They won't be exact, but they'll be close. Because again, we're using a linear approximation. All right, so I was able to actually get that error pretty quickly just by using calculus. So this is what I mean when I talk about error propagation and how we can figure out what potential error we have later for measurements that we've done along the way. All right, kind of seeing what I'm doing here? Yeah. And hopefully you see its relationship to linear approximations and how we're doing the same thing. We're using the fact that this derivative is giving us the slope of the tangent line, and we're using that tangent line to figure out the next step. There are a couple of terms, though, I need to give you so that when you're reading these things and they ask you to calculate something, you know what's what, because not all errors are the same. And so there are a couple different things that we look for. So one of them is what we call absolute error. And absolute error is how much you're off. All right, this is the I'm just going to put here the amount of the error. And in the context of all the symbols and everything, right? Like that would be this guy right here, the delta V. That's your absolute error. The delta X, that's your absolute error, just in volume versus length. Okay, so it's the amount of the error. So think of this is the delta X, delta V, delta R, delta whatever. Okay, so whatever the quantity is, that's that delta. That's the actual error that we're off. So that's the absolute error. Sometimes it's called the actual error. But the other thing that we're often interested in, and this is sometimes more important, is the relative error. And in the science world, this is what we tend to care more about. And relative error, what that is it's a measure of, well, how bad is your absolute error? Because not all absolute errors are the same. For example, we just calculated that the error in the volume of this cube is 1.875 cubic centimeters. Okay, is that good? Is that bad? Well, I mean, I don't know. If you just have a little die that's 2.5 centimeters on each side, I don't know, that could be kind of significant. But what if instead we are talking about the measurement of the volume of Earth? If I was off on my calculation for the volume of the Earth by 1.875 cubic centimeters, is that good approximation or bad?
Very good.
Yeah, it's very good. Like, so good that I should get the Nobel Prize for being able to do that or something, right? I mean, that would be incredible to be able to be that precise with something that large. Okay, well, what if now we're not talking about the volume of a die, but we're talking about the volume of a, let's say, the volume of a pinhead, right? So think about like a little stick pin, and you know how they make the little balls on the ends of those? What if we're off on the measurement of that by 1.875 cubic centimeters? Well, that's really bad, right? So if I just told you, oh, well, we're off by 1.875 cubic centimeters, the answer would be like, okay, is that good? Is that bad? I don't know. And that's what relative error gets at, is it tells you compared to the actual amount, how is this error doing? So the way that this is calculated is you take your error and you divide it by the actual value. Okay, so you would take whatever that number was that you calculated as your error, and then you divide it by what it really should be, like what the true value of this thing should have been. So in this case, if we wanted to find the relative error, it's going to be that 1.875 cubic centimeters divided by 2.5 cubed. Because remember, that was what the actual volume should have been, 2.5 cubed. So take your calculator, 2.5 times 2.5 times 2.5, divide that into the 1.875. Okay, so it's actually that actual error divided by that true value, what it should be. Okay, so Mariola, was that 15.625? Was that the 2.5 cubed?
Yes.
Yeah, okay. So you would take the 1.875 and divide it by 15.625. And that'll give you the relative error. So it's going to be less than, no, slightly more than 0.1. It's like 0.1, 0.12 something.
Mm-hmm.
Okay, so 0.12, blah, 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 blah. And these are usually represented as percents. So this would be a approximately 12% error. Okay, well, that would probably not allow us to stay in business for very long if we're constructing dice, because the 12% error is probably not good enough for what we want to do.
I got 0.016. Wait, oh wait, never mind. I put an extra one.
Okay. All right, so this is error divided by actual value, and we usually represent it as percentage. So we'll talk about what percent our error is. Okay, so in the context of the symbols and everything, relative error, it's going to look like this. It's going to be dv over v, or delta x over x, or delta t over t, or etc. So now you're not just dividing, or you don't have just your differential piece, your delta piece, but you're dividing it by the actual amount. Right? So that's what we did here. We took our delta V and then we divided it by V. So this is how you can figure out your relative error. But I want to show you something kind of cool. Well, always take it with a grain of salt when I say something's cool. But here's what's, I like this because you can actually figure out how the relative error, what the relative error is going to be in terms of the relative error of your initial error measurement, usually without even plugging in a single number. Right? Like we went through all this and we got, you know, the 12%. Let me show you that we can actually get that a lot faster without actually having to plug in numbers. Because let's use what we just did. It was delta V over V, right? That's how we're going to get the relative error in the volume. So it's going to be delta V over V. Now, the delta V, when we calculated that, remember it was the derivative, so 3x squared times delta x. So hopefully you remember, it's long since been erased, but it was over there, where we had delta V was 3x squared times delta x. Well, now let's actually divide by the volume. The actual formula for the volume is x cubed. So this simplifies down. We can cancel some of the x's. And so here we get 3 times delta x over x. All right, so remember what this is. This is the relative error in the volume. Now, this guy, delta x over x, this is the relative error in the length. And so what this formula just told me is that if you tell me how good my length measurement is, you tell me what % off it's going to be, I know that my volume is going to be 3 times that. So if there's a 10% relative error in length, there's a 30% relative error in volume. If there's a 2% relative error in length, there's a 6% relative error in volume. So let's backtrack this. You notice how we found out that the relative error was 12% in the volume? That tells me that the relative error in the length was 4%. And if you go back and you look at what we had an error of 0.1 centimeters with a length that was supposed to be 2.5. You can see really easily that that's 4%. So if we had started with that information, you told me that there's a 4% error in length. This then tells me, oh, there's a 12% error in my volume. And you notice that we didn't actually have to do any calculation. I mean, I guess we had to figure out what our initial % error was. But this is kind of cool that you can immediately see how this error is going to pass forward. Like in this case, going from length to volume of the cube, it triples our error. Now, will it always be triple? Of course not. It'll depend on what the structure is, what the thing is we're actually calculating. But you can use the calculus to do this. Maybe you see why I think that's cool. Basically, I think things are cool when it makes it so I don't have to work as hard. This is way easier. Oh my God, way easier, way faster. I don't have to do line division with decimals. I'm gonna multiply by 3. I think I multiply by 3. Right? So take it for what it is. All right, but there's another application of derivatives. Even though it really is the same, it's still a linear approximation. It doesn't feel like it, but it's still a linear approximation, and we're just doing it specifically with looking at errors and how errors propagate. All right, so I just looked at the clock. I don't really feel like going into the next topic because we're going to end up just kind of being in the middle. I'm going to have to recap it next time anyway. So what I want to do is let's actually talk about the exam that's coming up next time. So we'll spend just a little bit of time kind of reviewing, letting you know what to expect for it and all, because we do have an exam on Friday, right? So some things to know about that exam. Because we're having an exam, there will not be Zoom class. I'll still be on the computer. I'll be available. I'll be checking messages. I'll probably have the Zoom classroom up. So if you pop in, if you have a question, you can come in. Just realize that I might be doing other things, so it might take me a minute to respond, but I will definitely be available. But no Zoom. All right. So on Friday, it's going to be available at 8:30, as usual. But again, it must be uploaded by 11. So that's giving you 2 hours to do the exam and a half hour to deal with technology. So don't push it, right? I'm not giving you 2.5 hours for the test. I'm giving you 2 hours for the test and a little bit more time to deal with technology issues. So it needs to be uploaded into Canvas by 11 a.m. All right, but you guys know the drill. You took the first exam. You kind of know what to expect and how this is going to play out. All right, so first things first. So then no Zoom class again. All right, in terms of what it covers, it's basically a chapter 3 test. I know technically the first couple of sections of chapter 3 were on the first exam. But from there on out, it's just chapter 3. So that means no related rates and no like error propagation, linear approximation, none of that stuff. Okay. But it's all about derivatives. So things you definitely need to know, right, are the differentiation rules. So power, product, quotient, chain, so on, right? So we developed all kinds of rules. You need to know them, right? You need to know how to do the various differentiations. So that's a big part of this. I'm going to give you a function. I'm going to tell you, hey, find the derivative of it, or find the slope of the line tangent to it, or what's the rate of change in this thing, or however I phrase it. It's going to come down to, all right, and you need to differentiate it. Make sure you show me your steps. Okay, I am not satisfied with the miracle answers where here is the function, here's the answer. That's not what I want to see, because any kind of technology can do that for you. I want to see you showing me the steps. Okay, so make sure you show me your steps when it's just a differentiate. But other than the derivative rules, you also should know the derivatives of all kinds of functions. So let me make another list here. All right, so in there, of course, are polynomials. Those you're probably, they're old hat now, right? But polynomials, radicals, so square roots, cube roots, so on. the trig functions, the inverse trig functions, exponential functions, logarithmic functions, and combinations thereof, right? Things being multiplied together, divided, composed, and so on. But we now pretty much know how to differentiate everything. So make sure you know those derivatives because you will need to know how to use them. Other things that you should know how to do. Know how to do implicit differentiation. So that you don't actually have to solve for y. Because sometimes you can't solve for y, and yet we can still figure out slopes of tangent lines. So implicit differentiation gets its own little bit there. Also, inverses. So kind of like the one that was on that quiz, the most recent quiz. Know how to get the derivative of an inverse from the function itself. I'm feeling like this is about it. Let me grab my book so I can look at the table of contents. I just want to make sure that I'm not missing anything. But to my recollection, those are the big topics that come from chapter 3. Oh, okay. One more that I just saw. In terms of kind of an application, remember the whole like rates of change stuff? So I'm going to put here velocity and acceleration. How those are found. So like if you've got a position function, so if you got a function that describes where something's located with respect to time, if you differentiate it, that gives you velocity. If you differentiate it again, the second derivative, that gives you the acceleration. So be able to do that. Let's see, so velocities, rate of change. Yep, that's looking like that's about it. And that's pretty easy for me to say, right? Yeah, that's it. I mean, there's a lot here. There's definitely a lot here. But it's very similar to the homeworks and the quizzes. So hopefully it's nothing that's going to catch you off guard. All right. But I would basically break it into the 3 pieces. There's know the derivatives of the functions, know the different rules, and then some of the, I'd say more, I was going to say esoteric. That's not the right word. But they don't really fall into those 2 categories, but a couple of other things. So, but that's what it's going to look like. Again, it's open notes, open book, whatever. I mean, I can't control that when you're taking it at home, but make sure you show me your steps. And it is definitely not okay to be like, hey, Symbolab, what's the derivative of this function? And give me their steps, because I know those sites. I know when it's not your work. Show me your work. Okay, don't cheat. I don't want to have to give anybody a 0 on this test. It would really, really suck. Okay, so show me what you got. But yeah, there it is. So we have like 5 more minutes. If people have any specific questions or anything I didn't talk about here, I'd be happy to cover. Anything floating out there other than the general anxiety of an exam?
We're not doing relative, wait, what's it called? Wait, hold on, I'm looking at my notes. We're not doing, related rates, are we?
No.
Okay, thank you.
Related rates will be on the next exam.
Great.
That'll be where the next exam starts. But good question. All right, well, it's sounding like we don't have any other questions, so I'm going to go ahead and stop our recording here.